Hi there and welcome from Ventura, California to today's webinar, Precise Point Positioning, Part 2, A Deeper Dive, sponsored by Novotel and Inside GNSS, and hosted by WebAttract, the leader in thought leadership webinars. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders, as today's webinar is about hearing from these experts. Now, during part 1 of PPP that was held back in December of 2014, these experts discussed the leading high-accuracy GNSS techniques of real-time kinematic, or RTK, and PPP. Today, we'll explore PPP in greater depth. You'll also have an opportunity to have your questions answered at midpoint and at the end of the presentation during the Ask the Experts panel session. Now, we've invited you along with over 600 professionals registered from 50 countries across 29 states and provinces, representing a variety of industries. Over the next 90 minutes, regardless of your industry segment or your location, we're confident you'll find today's webinar of value. Before we do get started, Glenn Gibbons, editor and publisher at Inside GNSS, would like to take a moment to welcome you and to introduce Thomas Morley of Novotel, our sponsor for today. Glenn?
Thanks, Lori. And on behalf of the Inside GNSS team, including our business developer Richard Fisher and myself, I extend a hearty welcome to our international audience for today's web seminar. In just a few minutes now, we'll take up a subject that we introduced with an event last December, GNSS Precise Point Positioning. PPP is a category of GNSS techniques that uses state-of-the-art receivers and advanced signal processing to produce very high accuracy results. Before we begin, I just want to mention Inside GNSS's approach to these web seminars. We limit ourselves to no more than 6 webinars per year in order to allow the time needed for preparations to ensure the high quality of the content and presentations by our panels of experts. I believe that you will find that today's event provides an excellent example of that approach. So now it is my pleasure to introduce a representative of the sponsor for our webinar, Thomas Morley, the manager of Novotel's Applied Technology Group. Tom has earned quite a collection of academic degrees over the years, including a Bachelor of Science in Civil Engineering from the University of Manitoba and master's degrees in Geomatics Engineering from the University of Calgary and Engineering Management from the University of Colorado at Boulder. After working for a time as a GNSS applications engineer, Tom joined Novotel Incorporated in 2006. Since 2013, he has led the company's Applied Technology Group, where he is responsible for developing market and application-specific collateral for use by the Novotel sales and business development teams. Tom, welcome.
Great. Thank you, Glenn, for that introduction. Welcome, everybody, to today's webinar on precise point positioning. And again, this is part 2, a deeper dive. This webinar should be an excellent follow-up to December's webinar on precise positioning techniques. Today, our subject matters will aim to help you gain an understanding of the complex multidiscipline engineering problems that are encountered trying to convert GNSS signals into robust sub-decimeter level positions. Our goal today is for you to obtain a good understanding of the performance characteristics of precise point positioning. This will help you determine whether this exciting technology is suitable for your specific application or need. So on behalf of Novotel, welcome and enjoy the webinar. Back to you, Glenn.
Thanks, Tom. Now I want to turn the webinar over to today's main moderator, Demos Gebra-Egziaber. Over the years, Demos has helped develop and moderate numerous Inside GNSS webinars. In his day job, Demos is an associate professor of aerospace engineering and mechanics at the University of Minnesota Twin Cities campus. His research deals with the design of multi-sensor navigation and attitude determination systems for aerospace vehicles. Recently, his work is focused on multi-sensor solutions for operations in GNSS stressed and GNSS denied environments, including the use of such systems on unmanned vehicles. Demos, thank you for joining us again for today's event.
Thank you, Glenn, and thank you everyone for joining us this afternoon. We're glad you're with us. So before we dive into the subject matter, let us start with a quick poll to break the ice and to get the pulse of the audience. Lori, if you could put the poll up.
Absolutely. And everyone, you should see that coming up on your screen. In the next year or two, PPP services will be available to all. Is it on all GPS, GNSS receivers, for example, mobile, surveying, etc. Retrofitted to all receivers on newer high-end receivers only? Or what is PPP? And it looks like it's come in at 35% on all GPS, GNSS receivers, 9% retrofitted to all receivers, 52% saying on newer higher end receivers only, and 4% saying what is PPP? Demos, any thoughts on those responses?
Well, it's a good spread, and as we're going to see from the panelists today, it's PPP is a both software and hardware dependent approach. So without further ado, let me go ahead and introduce our presenters for today. And we have two panelists, and the first, I'll introduce them as they start their presentations. The first one is Dr. Sanjeev Gunawardena, who is a research assistant professor with the Autonomy and Navigation Technology Center at the Air Force Institute of Technology. Prior to that, he was a senior research engineer and principal investigator with the Ohio University Avionics Engineering Center, where he led several GNSS software receiver-based R&D projects. He earned his BS in engineering physics and BS as well MS and PhD in electrical engineering, all from the Ohio University. He holds several patents in the area of advanced GNSS receiver design, and his research interests include RF design, digital system design, high-performance computing, software-defined radios, and all aspects of GNSS receiver design and signal processing. Thank you very much for being with us, Sanjeev, and I will hand it over to you.
Oh, thanks, Demos. So, hello everyone from around the world. We are really thrilled about this opportunity to talk to you once again about precise point positioning techniques. As you know, enabling PPP requires a lot of work on both the receiver hardware and software sides, like Demos mentioned. Now, some of you may be wondering exactly what's different between the GNSS receiver inside your smartphone and one that's used for precision agriculture or a monitoring station. We went through some of those details in our previous webinar, which we encourage you to view offline. Anyway, to review, this slide highlights the antenna and RF front-end differences. And this, here are the differences when it comes to baseband signal processing. Fundamentally, all GNSS receivers perform timing measurements on the satellite signals that it tracks. The accuracy of those measurements relates directly back to the receiver's bandwidth. This in turn dictates its power consumption and cost. With that, let's focus on high accuracy applications such as PPP. In this deep dive seminar, I'll focus on receiver aspects needed to deliver the best possible range measurements, and then Sunil will follow on with measurement domain techniques that enable PPP. I'll start with the topic of nominal signal deformation and follow with front-end component effects. These two are closely related, and so is multipath, which I will cover next. Finally, I will talk about in-band interference detection and mitigation techniques. This time-lapse video shows high-resolution chip shapes for some GPS CA code signals. If you look carefully, you can see different wiggles on the signal for different PRNs. Note that what you're seeing is a composite of all the signal deformations that are due to the satellite's transmitter, its antenna, the ionosphere, and the receiver hardware. You can see that some of the wiggles are characteristic to the satellite. For example, PRN6 has more oscillations compared to others. PRNs 27 and 30 also have oscillations, but only for the negative chips. Now, I should stress that having these oscillations doesn't mean that the signal is flawed in any way. It's simply a characteristic of the signal generation and transmission hardware in the satellite. That's why we call it nominal or natural signal deformation. Most GNSS receivers don't process the signal at this level of detail because of complexity and power consumption. But the net effect of these wiggles impacts the measurements made by high bandwidth receivers and ultimately impacts the performance of PPP. Here are the measured pseudo-range biases that arise from natural signal deformation. As you can see, these biases can be as high as 20 centimeters between satellites. This is an issue for high accuracy differential systems, especially when two receivers don't have the same bandwidth and correlator spacing. For absolute positioning applications like PPP, natural biases can be compensated by long-term observations. Receivers could also correct for these using compensation values stored in a lookup table. But it's usually not that simple because natural biases can change dramatically when the satellite payload gets switched by the control segment to use a different hardware module. Now let's talk a little bit about how the individual components of a receiver can impact measurements. I will illustrate this using two types of IF filters. The first is a 70 MHz surface acoustical wave filter with 24 MHz bandwidth. This type of filter is used in some high accuracy receivers. The second is a 70 MHz LC filter. This type of filter is made up of discrete inductors and capacitors and is significantly larger and more expensive compared to the SAW filter. This block diagram shows the technique used to precisely measure pseudo-range errors due to component variations. We start by measuring the component's scattering parameters using a network analyzer. These S parameters are then used to model the component's impulse response. We then pass simulated GPS signals through this model and perform chip shape processing. The output is then phase rotated and used to form various code discriminators. Finally, these functions are used to estimate pseudo-range error as a function of correlator spacing for all 32 GPS PRN codes. These figures show how the computed impulse. These figures show the computed impulse responses. You can clearly see that the SAW filter has a very different response compared to the other one. The SAW filter converts the electrical signal into a mechanical vibration and performs all the filtering on this acoustic wave. By slowing down the propagation velocity from the speed of light to the speed of sound, SAWs deliver the performance of high-quality filters at a much smaller size and reduced cost. But as you probably guessed, things are never that simple. The animation shows what happens to the shape of the chips when perfect simulated GPS signals go through these filters. For the SAW filter, you get more wiggles and a peculiar effect that looks like something is happening before the chip actually transitions. We call this pre-ringing, and it had us scratching our heads for months before we finally figured out that it is due to the SAW filter's tapped delay line type behavior. This animation shows the pseudo-range natural biases, how they're colored by these filters. As you can see, the error envelope stays largely the same, but the SAW filter adds its own PRN-dependent biases because of its large in-band group delay variation. We have measured and found that these variations are on the order of 7 centimeters per kilohertz, which means you could also get centimeter level biases as a function of Doppler frequency. So to make a long story short, it's probably not a good idea to have transversal SAW filters in a receiver meant for high accuracy like PPP. Fortunately, most newer receivers almost exclusively use what's known as a direct conversion architecture that has no need for these type of filters anymore. This slide summarizes the amount of inter-PRN biases and device-to-device variation for various types of filters used in GNSS receivers. As expected, large and expensive cavity filters provide the best performance. For ceramic dielectric filters that are used in most high-accuracy receivers, you can expect to see a couple of centimeters of device-to-device variation. For RF SAW filters, expect to see large variations for absolute delay on the order of tens of centimeters. This delay variation has some impact on the navigation receivers, but must be really taken into account for precise timing applications. Now let's switch gears and look at multipath. As we discussed in our previous webinar, there are two ways to mitigate multipath. The first was antenna technology. where we use spatial discrimination techniques to try our best to keep multipath from corrupting our received signal. By and large, antenna technologies are quite effective at mitigating ground multipath. Let's look again at how multipath can be limited as part of the receiver processing. The animation shows how the correlation function becomes deformed when a single multipath reflection of half amplitude and about 100 meters delay is added to the direct signal. Remember that we estimate timing from this correlation function. Notice that the deformation is much less near the top of the triangle. So the effect of multipath can be reduced by reducing the correlator spacing. The figure on the lower left shows pseudo-range error as a function of multipath delay, better known as the multipath error envelope. Notice that short delay multipath is very difficult to remove. Each receiver vendor has their own patented technology to do their best at removing this. This slide shows the evolution of multipath mitigation technologies in the past 25 years. Today's state-of-the-art techniques implemented on high bandwidth receivers mostly eliminate multipath for delays greater than 25 meters and have reduced code multipath errors to less than about 6 centimeters for short delays. Generally speaking, high accuracy receivers reduce their measurement error and noise by keeping very tight lock on the carrier and code. The slightest glitch can upset this process and cause the receiver to slip a cycle, or in the case of the code, expand the tracking aperture to maintain lock. One thing that can upset this fine tracking process is interference. Interference comes in many forms, and I would encourage you to watch some of the previous Inside GNSS webinars to know more. On the topic of mitigating interference, let's take a quick look at this graph from Dr. Bastide's dissertation that shows ADC quantization losses. What this graph is essentially showing is that there's little benefit to having correlators that process more than 3-bit input samples. So to put it another way, anything more than 3 bits exponentially increases hardware complexity while providing very little added correlation gain. This means that the most efficient interference suppressing receiver architectures are the ones that sample the signal with extra bits to handle the interference dynamic range, but pre-processes that interference out before sending its 3 or 4 best bits into the correlator. Another point I want to make here is that as interference becomes more and more of a problem in today's crowded spectral landscape, it becomes more important for GNSS receivers to have built-in spectral situational awareness capabilities to inform the user about GNSS band quality. A handful of receivers have already started to integrate these functions into their products. This slide shows a relatively inexpensive way of mitigating most types of CW and swept CW type interference. The technique is based on what I like to call the crest riding technique, which was first invented by Amoroso for spread spectrum communications applications and was adapted for GPS by Logan Scott. The circuit also shows a simple jamming meter that can form the basis for a signal situational awareness capability. The distribution of CW-like interference is significantly different to that of Gaussian noise. So the Gaussian noise sample superposed on the CW signal can be extracted for correlation whenever the interference signal is stationary. In the case of CW, this is when the sinusoid is near its maximum and minimum points. The method involves detecting the onset of non-Gaussian distribution and setting thresholds to pick off the usable Gaussian noise samples for correlation. The animation shows this process in action. This slide shows the performance of that crest riding technique for interference to noise ratios of 50 dB. The left figures show how the receiver performs without any interference suppression. On the right are carrier to noise ratios when the crest riding technique is turned on. You can clearly see up to about a 15 dB improvement in interference mitigation performance. This table shows various methods that can be used to implement situational awareness. Some of these techniques require significant additions to baseband processing chips and are only possible for newer receiver designs. On the other hand, some techniques like monitoring AGC levels are available for free, and all it takes is a firmware modification. Take, for example, this block diagram for a poor man's spectrum analyzer. This can be implemented using one or more spare channels. All you have to do is turn off the CA code and feed a sawtooth function to the carrier NCO. This will give you a DFT output, which sweeps in time to produce a spectral situational awareness capability with only a firmware mod. Now you may be wondering how to turn off that CA code. Well, most SBAS capable receivers need to program what's known as the G1 and G2 registers to generate the extended set of CA codes. All one has to do is program those registers to all zeros, and this essentially disables the CA code generator. So with that, I'll hand it back to you, Demos.
Thank you, Sanjeev. So let's introduce our next panelist, who is Dr. Sunil Bisnath, who's an associate professor in the Department of Earth and Space Science and Engineering at York University in Toronto, Canada. His research interests include precise GNSS positioning and navigation algorithms and their applications. Previous to being at York University, Dr. Bisnath held positions of geodesist at the Harvard-Smithsonian Center for Astrophysics in Boston, Massachusetts, and assistant research scientist at the University of Southern Mississippi NASA Stennis Space Center. He holds honors Bachelor's of Science degree and Master of Science degrees in surveying science from the University of Toronto and a PhD in geodesy and geomatic engineering from the University of New Brunswick. Sunil?
Thanks very much, Demos. Hi, everyone. So following from Sanjeev's discussion on hardware, now we want to talk a bit more about GPS PPP, the algorithm side of the equation. And we'll start by just reminding ourselves the difference in terms of the concept of PPP versus the standard positioning service. Whereas for standard positioning, as most people use GPS, we're providing meter level orbit and clock information from the GPS satellites. One of the big differences with PPP, the first P, the precision part of it, is the access to precise orbit and clock information, so going from meter level to centimeter level in terms of those products. In terms of the actual tracking data, standard positioning uses the CA code typically, where PPP uses all of the code information as well as the precise but ambiguous phase information. In terms of filtering, standard positioning uses typically an epoch by epoch filtering process, whereas the data is processed sequentially in PPP, as well as there is additional error modeling. The result being this move from few meter level positioning that is typical with a standalone low-cost GPS receiver to decimeter all the way down to few millimeter level positioning with PPP, as we'll see. There are differences between PPP and RTK or network RTK, significant ones, that may not be apparent to many users who are standing out in the field or on their platforms with a high-end GPS receiver. Some of the main aspects to consider are listed here in this first column. If we talk about coverage, for example, PPP is typically global in the sense of how it is designed, whereas RTK, such as baseline RTK, is very localized, and network RTK is regional over a city or a region or a small or country. There are range limitations with RTK and network RTK because of the infrastructure requirements on the ground, whereas with PPP there are none, depending on how the PPP is designed and developed. So we can go through this list where we see that there are some differences and other differences, but I want to focus on the major limitation of each of the systems. And with PPP, that's the so-called convergence period. That is when the receiver is turned on to produce this decimeter to meter level, millimeter level solution requires time, usually a few tens of minutes to get down to the decimeter level, which is not the case with RTK, where we can get few centimeter level solutions very quickly. However, RTK has a limitation of range depending on the network infrastructure. So in this figure, we see a typical GPS PPP solution. This is static processing of a static site over the course of a day. And there are some classical components to this figure in terms of PPP performance. The first that we can see is in the first few tens of minutes, this convergence down to the decimeter level or better. And then over time, the next few hours, convergence down to a few centimeters. We have the horizontal and vertical plotted here. And then over the course of the day, very stable solutions, and then further convergence down to the few millimeter level. The final point to be made is that there are no data gaps in this solution, and if there were data gaps and the solution the filter had to restart, we would see a similar situation as we see at time 0 here. This reconvergence issue versus initial convergence will be discussed by myself further and Thomas as well. So the reason for this solution convergence issue in PPP, well, in this diagram we have the measurements that are collected in the range domain, the code and phase measurements, and they're collected and processed over time. We also, in the bottom part of the figure, show the position domain processing, which is a form of phase filtering of the code positions. The code provides the initial absolute position, and it is filtered over time with the precise but ambiguous phase measurement in typically a sequential least squares or extended Kalman filter processing technique. And over time, as the phase filters the code's positions, the position error goes down. And this is what causes that initial convergence period requirement for PPP. Another key aspect of PPP is its sensitivity to the measurements that are being used. Unlike RTK or network RTK, where we have 2 receivers or multiple receivers respectively being used and the measurements from those receivers being used in the processing, with PPP we are typically referring to the measurements from the single receiver. And what we can see are 3 examples from 3 different stations, again, 1 day static processing, and we see quite different results. Quite wonderful results here and very stable over time. A little noisier here, but fairly stable over time in this case. And in this situation, convergence takes quite a bit longer, and then we see some divergence over time. Why are these things happening? The particular receiver, the local environment, multipath effects, the quality of the code and phase measurements being used, perhaps interference, as Sanjeev referred to, and as well the geometry of the measurements that are being made. So very much measurement dependent process. We can see that again in this figure where we have 2 stations in Southern California that are less than 10 kilometers apart, and we have 7 consecutive days of solutions, the entire time series of the solutions. In the station on the right, we see very nice convergence and quite similar solutions from day to day, where just a few kilometers away, we see quite different solutions from day to day. And again, these are very localized effects that are causing these issues. Now, they would exist with any GPS data processing. However, with PPP, with a single receiver, we see the direct influence on the positions. In this figure, we've taken data from a week of 300 globally distributed sites, so a great deal, very large data set. And we're looking at the 5%, the top 5%, the best data, and the bottom 5%, the worst data. And what we see with the very good data is this incredibly tight set of positioning errors or solution accuracy of just a few millimeters. But even with the worst data, we're looking at a few centimeters as well. So quite well behaved if we take a look at a very large data set. Now, if we move from this conventional PPP solution, GPS PPP solution, to trying to make improvements to that, what has been done over the last few years is a lot of research to resolve the integer ambiguities in PPP, because we're directly measuring and then estimating the phase ambiguities. Unlike with double differencing, in PPP, what we have are a number of biases that we have to take into account that makes the process much more difficult. And we want to try to resolve ambiguities because there are a number of potential benefits. One, to reduce this convergence period characteristic of PPP, produce higher quality results, more consistent solutions, and make it overall a more robust processing technique. Initial attempts at fixing these ambiguities did not work too well. And the main reason having to do with, here's an example of where they are, and these are on the ionospheric free code and phase measurements. We have satellite and receiver fractional phase biases that exist. They cancel out in RTK when we're making measurement differences between receivers. They do not in PPP. So the question is, how do we resolve these PPP ambiguities without any assumptions on their behavior? A number of techniques have been developed and implemented. These techniques there are slight differences in their assumptions, but they're on some level equivalent. For example, the integer clocks and decoupled clock models, they reparameterize the observation equations that we showed in the previous slide to isolate the code biases from the ambiguity estimates, and the result being that the code the result are what are called code clocks and phase clocks. So we actually take the phase ambiguity and we couple them with the phase clock parameter to essentially have two different clocks. Also, there are methods to mathematically combine measurements to amplified wavelengths to make it easier to distinguish between one ambiguity term and another. The uncalibrated hardware delay approach computes offsets from clock products to allow the user to access the integer ambiguity terms. What's being done in the background is a great deal of processing from a network of reference stations to determine some of these biases at the satellite end, and they are additional products that are then sent to users along with the satellite orbits and the satellite clock information, so that the user can then produce a PPP AR or ambiguity resolve solution. What does that give us? In this slide, what we see are, if we just focus on the red lines, the solid red line is the float horizontal solution, and the dashed red line is the fixed horizontal solution. This is a log-log plot, 24 hours from 1 millimeter to 1 meter of error. And what we see at the outset in the first few tens of meters is that resolving the ambiguities does not really help us very much. When more and more data is introduced into the processing filter, we then estimate the correct ambiguities, and the fixing produces a significantly improved solution. And over time, the float solution approaches the fixed one. So ambiguity resolution does help. It does help over this period, but it doesn't reduce significantly the initial convergence time. The same thing is the case with the blue lines for the vertical component. Another improvement that has been made over the last few years is applying ionospheric constraints. What has been found is that if we estimate the ionospheric delays, let's say before a vehicle carrying a receiver goes under a bridge, then we lose lock when the vehicle comes out from the other end, the underside of that bridge, a few seconds or tens of seconds later. Those ionospheric estimates are still mostly valid, and if we use them as a priori after the data gap, it allows for very quick reconvergence. It doesn't help with the initial convergence, but the reconvergence of the solution. And we see that in this example, where this is the standard or conventional PPP, where every hour we've reset the solution, that is, let's simulated a data gap, and we see the initial convergence sometimes better, working better in 1 hour than another. Whereas with a PPP ambiguity resolve solution with the ionospheric constraints, it performs almost seamlessly, and we get quick reconvergence because of that. Thomas will talk a bit more about this in one of his case studies. But with that, I'd like to pass it back to Demos for the next segment.
Thank you, Sunil. All right, so at this point, we're going to pause and let you weigh in and ask questions to our panelists. And questions have been coming in, and please continue asking questions as we go through this webinar. So with that, let me start with the first question, and this question will be for Sanjeev. And the question is, could the control segment give us information about the PRN biases, or information that would help us with the PRN biases? For example, tell us something about the payloads on them, on the satellites, or something to that effect. What's your thoughts?
That's a good question. So, in principle they could, but the underlying thing is that these signals, even though they have these very subtle variations, they're still, like I said, they're still in spec. So one good example of this is, even if the control segment were to give us those biases, so consider what happened to SVN49, which was like a very severe case of signal deformation, right? So what they tried to do in effect was to do some corrections with the data message, with the ephemeris, to try to minimize the effect of that bias on the receivers. But the impact that it had was that that correction manifested itself differently in different receivers, because different receivers have different bandwidths and different correlator spacings and correlator types and so on. So really, even if the short answer is, even if they did, it wouldn't help much, because it really depends on the receiver architecture. Now, Sunil kind of alluded to this. So the better way is to have like a monitoring station, and then like figure out what these biases are, and then somehow translate that back and send it into the users as part of that precise ephemeris and all the precise information that the receiver gets through a different channel to implement PPP.
All right, that's an extensive answer. Sunil and Thomas, anything you want to add to that, or do you think Sanjeev covered it all?
Well, I would say Sanjeev gave a very good answer to that, and what we tend to do on the software side is from the reference stations to estimate as many of the biases as we can, and we'll talk about that in the second part of the presentations. But we do estimate as many of them as we can.
All right, great. All right, so let's see, second question. This one is for Thomas, and the question is, what is the magnitude of the errors contributed by the various biases that Sanjeev talked about in the data and the PPP data processing? Are they significant, or can they be ignored?
Oh, that's a really good question. Now, I'm not a hardware expert. Most of my expertise is in the algorithm side of the equation, so maybe I'll talk a little bit about some of the error sources that come in as a signal propagates. And I hate to be wishy-washy, but when I say is it significant, the answer would be maybe, and can it be ignored? I think the answer also is maybe. And it depends on ultimately how accurate you're trying to get your end solution, how robust your algorithms are, and ultimately what your intentions are. A lot of the biases are time varying, so you can't just estimate them once and forget about them. You'll have to continually reassess what they are. Some of them are, again, in the order of millimeters. Some of them are a couple decimeters. So again, if you're trying to get down to a sub-decimeter level solution, I would say ignore the decimeter level biases at your peril.
All right. Sanjeev or Sunil, anything you would like to add to that, or?
Well, so one diagram in that my presentation kind of showed that some of those inter-PRN biases can be at the centimeter level, and again it depends a lot on the receiver architecture, but Thomas gave a good answer. So really, I mean, it depends on the application, and like he said, the decimeter stuff, you choose to ignore it at your peril.
Okay. All right, so let's try to do one more question before we go back to the next part of our presentation. So this one let's see, it's going to be for Sanjeev, and if Thomas and Sunil, you could pipe in if you have comments on it. But what is the impact of antenna design in regards to accuracy on PPP?
Yeah, so this is a good question, and actually in the previous webinar, Sandy Kennedy from Novotel, she actually covered this at some level of details, but basically it really comes down to the phase center and the stability of that phase center, because obviously you could have variation with respect to temperature and so forth, and then also for different frequencies it's important that the phase center is kind of calibrated for all the different frequencies that you're intending to use. And then also Sandy kind of pointed out that the gain pattern of the antenna. So she showed this really good example where there was this one antenna that had a kind of a drop in the gain at like 45 degrees elevation, and that actually really impacted the performance of PPP because of that gain depletion. And then she compared another good antenna that had a very smooth gain pattern, and you could really see the difference of the PPP performance with respect to those two antennas. And then also obviously the azimuth, the stability across azimuth angles is also somewhat important.
Right. Thanks, Sanjeev. I hate to cut us short here, but we need to get on to the second part of our presentation. But we'll come back at the end to have discuss these questions. So keep the questions coming in. So let's move on to part two of our presentations. Before we do that, let's take a poll. Can you put the poll up, Lori?
Sure thing. Coming up on your screen, you should see our second poll, and we'd like to hear from you. Performance-wise, accuracy, integrity, which one do you think is true? GPS plus GLONASS PPP is equivalent to GPS only PPP. GPS plus GLONASS PPP is better than GPS only PPP, or GPS plus GLONASS PPP is worse than GPS only PPP. Or perhaps it's not that simple. Looks like we've got a front runner there, 57% saying GPS plus GLONASS PPP is better than GPS only PPP, followed by it's not that simple. Demos, any thoughts here?
Well, again, it's as we'll see in the next part of this webinar, that's exactly the problem we're going to be looking at, is what does one get from using other GNSS in the PPP solution. So with that, let's move on and bring up Sanjeev again to talk about high accuracy GNSS and its relation to PPP. Sanjeev?
Yep, thanks, Demos. So let's talk a little bit about GLONASS. So I will address the complications associated with GLONASS measurement processing, and then Sunil will discuss how this impacts PPP. So today, if you want additional range measurements to increase availability and your geometry, the obvious choice is GLONASS, because that is the only other fully operational GNSS besides GPS. And then also, unlike GPS that only transmits the civilian L2C signal on the newer Block 2RM and 2F satellites, all the GLONASS satellites have an open signal on the GLONASS L2 frequency. So civilian users can get iono-corrected measurements for all of the GLONASS satellites. But the issue is this interchannel bias problem. So because the GLONASS signals use FDMA modulation, each signal undergoes a different delay as it passes through the receiver's front end. So this slide shows various techniques that can be used to compensate for those interchannel biases. The simplest approach is just to perform a factory calibration. So now some geodetic grade receivers compensate for these biases by having what is essentially a built-in group delay meter. So that is, they inject some sort of very low power signal directly into the antenna and measure the magnitude and relative phase variation as a function of frequency. So they do this dynamically. So this is very similar to how a network analyzer works. With this technique, manufacturers can compensate for GLONASS interchannel biases at the sub-centimeter level. So having said that, this closed-loop measurement technique can only be implemented efficiently when the antenna and the receiver electronics package are co-located. That is, we are talking about what's known as smart antennas. So this technique would not work well if you had, the antenna with a different long cable. Now, this slide shows the GNSS spectral landscape that we will have when Galileo, Beidou, and the other regional systems become operational. So having 30 plus satellites in view at all times is very exciting for high accuracy applications like PPP. But with more inter-system signals come more complexity. So Sunil will talk about the complexities associated with different reference frames, different ephemerides, and so on. What I want you to appreciate from this picture, though, is the fact that these signals have been very carefully designed to minimize inter-system interference. Most use binary offset carrier modulation to spread power to the edge of the bands to get that inter-system spectral separation. But the band edges are also where the receiver's front-end filters have the most group delay variation. So we can expect these centimeter level inter-PRN biases that I showed you at the beginning of for GPS CA code signals to potentially increase for other GNSS signals. But then again, there are other factors to consider, like the fact that these new satellites employ digital modulation techniques and a different type of power amplifier in their transmitters. So like I said before, these things are never that simple, and that's really why this stuff is so interesting. So with that, I'll hand it back to you, Demos.
All right, thank you, Sanjeev. And now Sunil will talk about the algorithm side of GNSS PPP. Sunil?
Thanks very much, Demos. So following on Sanjeev's brief introduction, when we move from GPS PPP with ambiguity resolution and ionospheric constraints, when we move from those complexities to multi-constellation PPP, there are clearly benefits. Since PPP is a measurement-sensitive technique, more measurements and varied geometry will mean improved positioning, and that's what we do see. However, there are costs to the complexity of the differences that Sanjeev referred to, especially in his last slide. Some of the main issues are that different constellations use different spatial reference systems. So coordinates are referred to different references in different systems. The same is true with the temporal reference systems used. So the timing could be slightly different. For some users, there may not be a great effect, but we still have to estimate or model or somehow to manage or take into account these differences, which we can do. One of the big issues with GLONASS is that it's an FDMA system versus a CDMA, and Sanjeev had referred to issues with biases from frequency to frequency as the different frequencies go through all the transmitting and receiving circuitry and electronics. Also, we have many of the equipment biases that exist in a single system. So now when we talk about multiple constellations, then we're talking about many different equipment biases of different types that show up that we need to handle in some way. About these equipment delays are sometimes referred to as hardware biases, hardware delays, instrument delays. Well, basically we're talking about errors that are, well, errors, I should say, but delays that are introduced in the equipment through circuitry and electronics. And this exists at the satellite end, at the transmitter, and at the receiving end, at the receiver, through the antenna and receiver electronics. Some of these delays are estimated by tracking networks, as referred to by one of the questions earlier. Others are modeled. Many are often combined with other errors. And we have many different types of delays. Delays between codes, between phases, between phase type measurements, between frequencies, etc. Here are some examples for the GPS constellation. So given the complexity, the availability of additional signals is very tempting. So we are now in a world of multi-constellation PPP. Here we have an example of solutions, again, static processing over the course of a day. What we have in red are the GPS results, GLONASS in green, and in blue the GPS plus GLONASS processing. We see the classic convergence and then nice stable solution. GPS performs quite well in red. What we see with GLONASS is a longer time to convergence, and then a little less stable over time in this one example. However, what we see in blue, and I'll highlight the blue here, is overall faster convergence when we have GPS plus GLONASS. In terms of the quality of the solution over time, the solution was quite good to begin with GPS. GLONASS is providing us with faster convergence, which is very nice to see. If we take a look at a large data set, in this case it's 1 week from 350 global stations, again, static processing of static sites over the course of the day, and we look at the coordinates produced at the end of the day, we have some histograms of horizontal error at the end of those daily solutions. And we see in blue the GPS only solution. We see very nice performance. Here's the histogram here. With GLONASS, the performance is not quite as good as expected. There are more GPS satellites for one reason, so the geometry ends up being better. But when we combine GPS and GLONASS, we see that 95% of the solutions, and this is well over 2,000 solutions, are at 2 millimeters or better at the end of the day. So really terrific performance. We see something very similar with the vertical, slightly less accurate, but again, it's the inherent nature of GNSS. Now, we see those great benefits. However, going back to the issue of biases, here's an example of pseudorange interchannel biases for GLONASS, so that what we have on the x-axis are different frequency channels, that is, each satellite's transmitting at a slightly different frequency, and we see the few meter level interchannel biases on the pseudoranges. We have 8 stations here, and we see how from frequency to frequency, that is GLONASS satellite to satellite, how those values change. Now at these 8 stations, we're using the same type of antenna, but different receiver types, different firmware types. So many of the ideas that Sanjeev had brought up about correlator spacing, design of the receiver, etc., they're showing up here. And we have these issues, which is a problem with homogeneous or heterogeneous networks, whereas homogeneous networks, we wouldn't see the problems being so significant. We can carry on for a long time with PPP, but I'll end with this slide, and that's to say that multi-GNSS signals have enhanced PPP and RTK performance. Most RTK networks are now GPS and GLONASS enabled. The same with PPP, including ambiguity resolution and reconvergence, have started to appear commercially. Thomas will talk some more about that. Fast RTK-like initialization for PPP is still the ultimate goal, and there is still much work to be done. The integration of PPP with network RTK solutions, early 4-constellation results that show further improvements, triple frequency GPS results from simulations that show very fast convergence. So the future is very bright for PPP. So with that, I'll pass it back to you, Demos.
Thank you, Sunil. All right, so our final panelist is Thomas, who will, I guess, tell us about some real-world applications of, or evaluations, rather, of PPP. Thomas?
Great, thanks, Demos. Today I'd like to basically start where Sanjeev and Sunil have left off, which is take all of the hardware design for the antenna and the receiver and all of the algorithm design, put it all together, and evaluate what you get at the system level out of the black box. What does your, typically for this presentation, horizontal positioning actually look like with PPP? I want to touch on the actual antenna motion versus the processing technique that can be used. Talk a little bit about Novatel's dynamic evaluation methodology and why we go to all this effort to come up with a good trajectory in real time, and then focus on our real world results. Again, pretty much dynamic the entire time, but look at how does PPP perform under quite benign open sky conditions, then push the envelope a little bit and show some operation near trees where we have a lot of partial obstructions of the satellite signals, and then finally operation near and through a 625-meter tunnel that's within about 2 kilometers of the Novatel office here in Calgary, which completely obstructs satellites and the PPP L-band signal for about 30 seconds. This matrix basically shows on the horizontal axis you can have the actual motion of your antenna, can be stationary or it can be dynamic. Likewise, your processing technique that can be used, you can tell your algorithm, I'm static or I'm kinematic. And the terminology can be fairly important to keep consistent. Our previous presenter spent a lot of time talking about a very particular subset in this matrix, which is a stationary antenna and static processing. And with that, you can definitely get down into that sub-centimeter results as he showed. You also have the option with a stationary antenna to tell the algorithm that you're not static, that you're actually moving, and process the data as if you were moving. Likewise, when you're dynamic, you pretty much are forced into a processing technique that's kinematic, because you will run into a lot of problems if you are actually moving, but your processing algorithm thinks that you're sitting still. Now, why is this important? Well, for Novatel, virtually all of our customer base that is interested in PPP resides in that top right box. They're on vehicles, they're on things that are moving, and that is where they expect PPP to perform well for them. So we spend a lot of time in our company in that top right box. So here's an example of a fairly typical field evaluation that we did. This particular photo was back in August of last year. And what we end up doing is we take an RTK coordinate that's generated through our GPS inertial technology called SPAN, and we combine that with the inertial information that's all referenced to the IMU, or Inertial Measurement Unit, center of navigation. We combine that with the physical lever arm measurements, so the delta up, down, and east, up, down, and north. I'm going to get that wrong again. Up, north, and east to the actual phase center where the antenna phase center is located for all of these other antennas. And effectively what that does is it translates the RTK coordinate to all of the various antennas or any point that we're interested in using the attitude information from the inertial. From a campaign that we did in South America in December this year, this gives you an idea of the number of receivers that we put on a single machine. I've circled everything here that was running in a PPP mode, so we had at most 11 different receivers, some of them Novatel, some of them competitive, all running in a real-time PPP. And that's what the focus of a lot of this presentation will be on today. Now, the first test was in a benign open sky environment. This is the trajectory of the machine. It was about 4 hours of data. The machine was moving at around 6 to 10 meters per second, so a fairly good pace. And when we look at the time series for clarity, I've only included about 6 of the solutions here. But when we look at the time series, you can see at the beginning, the solutions start at that around a meter level and fairly rapidly converge down. Now, what's interesting here is I say everybody pretty much converges to sub 20 centimeters. There is one receiver in here that just did not like performing very well when it was dynamic, and that's the blue receiver. If I just get rid of that receiver for the next slide, this gives you a really good indication of 5 different PPP solutions, open sky, dynamic conditions, that everybody converges down to around that decimeter level or better. Really good performance across the board, and I was really pleased with how everybody performed in this. So I'm quite confident in how PPP works as a technology. I also wanted to show the first hours worth of data for 4 different receivers that went through a complete convergence from power on all the way to a steady state mode at the end of the hour. Again, everybody starts in that 0.5 meter to 0.7 meter level of accuracy, and everything converges to, here I put sub 20, realistically sub 10 centimeters in approximately 30 minutes. But the other thing that's very interesting is every manufacturer, every algorithm has its own determination of when the solution is converged. It has no knowledge of what the actual error is. It has to look deep into its statistics and come up with an estimate to say, I'm happy with my solution, I'm converged. If I overlay when the various solution types actually tell you they're converged, you can see that there's quite a variation between these 4 receivers. The brown receiver is the most aggressive and says I was converged first, when in fact it still had a little bit of work to do. The black receiver may be a little more conservative, but its actual error was pretty close to what is being promised with a fully converged PPP. So again, everybody will behave slightly differently. Not that one's better than the other, just different design considerations and slightly different performance. We also put PPP into a slightly more challenging environment where we spent more time driving along the tree lines. And again, this is to try to create some challenging conditions where there's some tracking interruptions of the satellite signals. Very similar performance for most of the receivers. I've put on the bottom axis where every time we drove past the trees, where that occurs. And you can certainly see this blue receiver got extremely noisy whenever we were near trees. So again, I'll get rid of the blue receiver. And again, generally, everybody worked really well in this environment. There were a couple, the teal receiver had a couple instances where the PPP engine popped out of a converged mode, but fairly rapidly came back. But overall, a little noisier than in a pure benign open sky, but quite solid, quite good performance. Now what's interesting at the very end of the data, I can blow that up a little bit. It just so happened the very last time we went past the tree lines, something happened to a bunch of the receivers. The pink receiver that had been running at a 5 centimeter level solution just slipped out to about a 60 centimeter solution, but the flag kept telling me that the receiver was in a high accuracy mode. A couple of the other receivers went into a low accuracy mode and started to reconverge. And a couple of the other receivers, like the black one and kind of that ochre color receiver, generally did pretty good and didn't exhibit the same kind of behavior. The takeaway from that, operating near trees can be a real challenge, and this is where there's the art and the science of dealing with the exceptions with the algorithms, and some receivers perform better than others. The last real-world example I'd like to touch on is driving underneath the airport tunnel here in Calgary, which is 625 meters long. Open sky to the east and open sky to the west, and it took our test vehicle around 30 seconds to go through that tunnel. So quite an abrupt and relatively long duration outage. Now, a couple takeaways here. The same pink receiver that we had in South America, in Calgary, produces a position solution that is inconsistent with all of our other PPP solutions. I have no explanation why, but we've observed this in Calgary, we've observed it in the Midwest US, and we've observed this in Europe. The other receivers, everybody starts off converged, and you can see right around time 5:14,000, we hit the tunnel for the very first time. Now, what's interesting is the pink receiver shows that even though it's biased, it does have a very rapid reconvergence characteristic. Same with the receivers at the bottom, the red and the black, both reconverge very quickly. The brown receiver is forced into a PPP reconvergence. So this is a really good example showing that PPP loves an open sky environment, and depending on your implementation, if you drive underneath or underneath an obstruction, this brown receiver is forced to throw everything away and start its convergence all over again. So that may be critical to your application. It may not be critical to your application. So in conclusion today, PPP convergence to that decimeter level accuracy can take tens of minutes. Rapid reconvergence is certainly a reality, and it can work really, really well. And overall, I would say the dynamic performance of PPP that I've observed in several different campaigns all over the world really is quite good. It's based on many days of testing in many different environments, many different conditions, lots of different flavors and manufacturers, lots of different solutions. Some are noisier than others. Most of them provide a really solid, reliable decimeter level solution. But again, the environment is very important for PPP when you're operating near trees or you're operating near overhead obstructions that can limit your satellite signals. Those are corner cases that have to be dealt with one by one. That's all I have. Back to you.
All right, thank you. All right, so we've got quite a few questions. We'll try to address as many of them as we can in the short time we have. So the first one, Sanjeev, I'll direct this one at you. And the question is, would the use of GPS, L2, I guess GPS and GLONASS L2C signals be beneficial in PPP?
Yeah, so that's a good, interesting question. So in the case of not having L2C, high accuracy receivers had to do something called semi-codeless tracking to actually make a measurement on the L2 component of the signal, because the code on L2 is encrypted, and so since there was no civilian signal, they had to do this semi-codeless tracking. So that process, you can get some measurements on L2, but it's pretty noisy because you have the squaring losses. And so arguably now that there is an open signal, L2C, you can do a much better job at that and hence estimate the ionosphere a little bit better with the newer satellites. And then also L2C has additional modernized functions in the signal. For example, it has a pilot component that allows you to perform long integration and hence get the measurement noise down. Those are some of the benefits that you can get by having L2C for GPS. And similar reasons also apply for GLONASS in that case.
All right, thank you, Sanjeev. Question number 2, Thomas. This one I'll direct at you. And I guess the person asking the question wants to know: can you list the number of applications where the PPP centimeter and sub-centimeter level is so important that it will have a big impact?
Sure. A lot of the applications that Novotel deals with are customers who are building equipment for autonomous vehicles, whether it's safety of life or robustness, or there's underground infrastructure, and maybe they're digging or doing something where they don't want to destroy what's under the ground. They're really chasing a good, reliable centimeter level solution. That would be a good example. I think where certainly chasing centimeters is important.
All right. Would Sunil or Sanjeev, any applications you can think of that you would want to add to this that you know of?
Oh, sure. There are the serving applications related to what Thomas was talking about, but whether it's cadastral serving or the type of serving applications in engineering construction, a lot of the offshore positioning applications for seafloor mapping, and of course all the scientific work that can come up, plate tectonics, etc., and to some extent the precision agriculture at the few centimeter level as well.
All right. So let's see. Next question. I will direct this one at you, Sunil, and it's an RTK PPP comparison. So roughly at what baseline length does post-process PPP solution outperform a traditional base station-based double difference solution, assuming no dropouts of data? I guess a fair comparison.
Well, I hate to respond by saying that depends, but it really does depend on the I guess the main factor I would say is time. I mean, if we're talking about a few kilometer baseline and you're trying to produce a solution in under 5 minutes, well, RTK or traditional relative positioning will be able to outperform PPP. If we take a look at a few kilometer baseline over many hours of processing, then there isn't actually that much difference. The other issue, of course, is the ability to do relative positioning. So if someone's far offshore, or if they're in an aircraft or a spacecraft, for that matter, on board a satellite trying to position a satellite's orbit, for example, in many of these applications, the baseline lengths are very long. So if we imagine mapping applications or many kinematic applications where we just have these infrastructure limitations, then in that case, that's where we see great benefit of PPP in open sky areas without any range constraints.
All right. Thanks, and Sunil. Let's see. Next question. I think this one I'll direct at Sanjeev. And I guess Thomas and Sunil, you could pipe into afterwards if you have comments. How could we actually estimate the inter-channel and inter-system biases in order to improve solution accuracy?
Okay, so I kind of went through some of that. So in the case of inter-channel biases, that method of injecting a signal and measuring, that's a direct way of doing that. And then also some of the stuff that I showed in the slides really are looking at very high precision techniques that you can, that kind of use signal processing techniques which are generally not implemented in receivers. So really, when you consider the receiver, it's outputting the measurements. So I guess, kind of Sunil alluded to the methods where you would have to, observe those measurements over longer times and then kind of have that convergence that has to happen. So Sunil, do you want to kind of comment on that?
Sure. There are many different biases. So, for example, if we had one slide about GLONASS inner channel biases for the pseudoranges, also for the phase. There is what Sanjeev's discussed, and then on the software side, and I'm sure Thomas can comment as well after, is that we can then through parameterization of our functional models and the processing, isolate many of these biases and estimate them. Keeping in mind, as Thomas had said, that many of the biases do vary over time. So we can average over hours or between stations, etc. But we do have to be careful that to talk about the magnitude of many of these errors and also the time variation of them, and that shows up in the ambiguity resolution algorithms that we see in different PPP techniques. But it can be done in many cases, but it's just further complexity in the algorithms.
All right. Anything you want to add to that, Thomas? Or
no, I think that was well done.
All right. All right. So the next question actually is for you, Thomas, and it's a question about whether you can comment on the truth system that was used and accuracy, etc., for the data that you showed on the real-world PPP.
Sure. So we used a very high-end inertial, which gives us very, very good attitude information. Combine that with our RTK engine into our SPAN RTK setup. In order to ensure that our data was solid, we did several things. Number one is we had our base station set up within about 300 meters of where our machine is operating, again, to limit that baseline length to try and minimize any of those spatially decorrelated values. We also, with recorded data, we have then the luxury to be able to go forwards and backwards through the data, which allows us to bridge any outages by approaching it in two different directions in the time domain. We also compared the SPAN post-process trajectory against our own RTK trajectory. So we used all the lever arms and everything to translate to another antenna that we had on the machine that was our own solution, and made sure that the RTK solution and the post-processed fused GPS inertial solution were all in agreement. And then we also basically did a voting where if all receivers did something odd, that's a strong indication that it is something to do with your trajectory information. If only one receiver does something odd, then that's a strong indication that it's an event that's unique to that receiver.
Right. Thank you very much, Thomas. Let's see, next question. This is going to be for Sunil, and I guess one of the viewers of the presentation wanted to know, looking at the graphs you were presenting, that the GPS PPP, GLONASS PPP, and GPS plus GLONASS PPP comparisons, that the GPS-only PPP solutions seem to be better, and is the viewer misinterpreting those graphs, or is there an explanation as to what they were seeing?
No, the viewer was right on, Demos, in the sense that what we did see was quicker convergence with GPS PPP versus GLONASS only PPP, and we saw more stability over time and better daily positioning results for two main factors. One, there are more GPS satellites in the sky in the GPS constellation than the GLONASS constellation right now. Even though they're fully operational, there are a number of extra GPS satellites flying above us, which, given that PPP is very much a measurement-intensive technology, the more measurements with better geometry, the better the solutions. And the other reason is because of some of these biases and the effort it takes to process them and to basically manage them in the processing, that also degrades some of the GLONASS processing solutions, because we need to compensate for a number of other errors in GLONASS. So we do see that difference, and I should just remind everyone again that when the two are combined, we do see some very nice results.
All right, thank you very much, Sunil. Let's see, next question. This one is for Thomas, and I guess it's kind of a follow-on to a question I was asked earlier. And it is basically, will PPP replace RTK in the near future? I guess, are they the one and the same thing, or I mean, what is the future of RTK versus RTK and PPP?
Good question. I don't want to say it will. RTK will never be replaced by PPP, because if you look at the history of RTK, 30 years ago, people would have looked at you as if you were crazy had you proposed that I would be able to do 50 hertz positioning 20 kilometers away down to a centimeter level. I guess the other word there is, can it replace RTK in the near future? For me, a lot of it comes down to what your requirements are. If you have an application where you're happy with 30 centimeters, 20 centimeters, and it's not a critical parameter, or you can afford some time to converge, PPP today may already be equivalent as RTK for that particular application. But RTK does have some performance characteristics that really set it apart and make it the gold standard, and that's that nowadays near instantaneous ability to resolve those double difference ambiguities and have that quantum shift from half a meter down to a couple centimeters in just a few seconds. I think that's a really high bar that PPP will struggle to get to, but I certainly don't want to sit here and say it'll never happen.
All right, Sunil and Sanjeev, do you want to look into your crystal ball and say something about RTK versus PPP in the future?
Well, I'd follow up on what Thomas said by saying that it was a great answer. I think that's the situation now, and where things will be in the next few years. Though, as we keep adding signals and going back to Sanjeev's graph of the multi-constellation processing, I mean, RTK works extremely well. It's a mature technology, and what we're seeing with PPP is that as we keep adding signals, we get better and better processing results, and we'll see more of that over the next few years and well into the next decade, given the launches that are coming up.
Sanjeev, anything to add to that, or?
Yeah. So like Thomas said, ultimately it really comes down to requirements. But then, having said that, kind of looking at the problem in terms of the receiver design space, technology is always moving forward. It's becoming easier and easier to implement, receivers with higher and higher bandwidths. So all that is, really helping to push the technology forward. And so, as technology progresses and algorithms progress, things become better, obviously.
All right, thanks. Well, I guess time flies when you're having fun, so we're kind of out of time here to answer more questions, and thank you very much for those of you that sent in questions, but we have to move forward at this point if we haven't answered your question. All right, with that, Lori, I'll hand it to you.
Absolutely, and before we do wrap up, I wanted to take a moment to invite Thomas Morley, our sponsor from Novotel, to leave us with a brief word. Thomas?
Great. Thanks, Lori. Thanks. I hope our global attendees found today's information on precise point positioning to be helpful and hopefully thought-provoking. I'd like to thank all of our panelists for sharing their expertise and information today. And finally, Novotel has been designing technologically advanced high-end GNSS receivers and antennas for over 20 years, and you're all invited to refer to our website for more information on our product line as well as information that we post on technical papers and case studies. Again, on behalf of Novotel, thank you for attending today's webinar. And back to you, Lori.
All right, and just to add to that, I'd like to thank our logistics producer, Patty Van Hooser, and for the behind-the-scenes collaboration and support. Most importantly, thank you for joining us. This is Lori Dearman saying, hope you have a great rest of the week. We'll see you on the next one.